We're now going to look at fluid dynamics. Now, up to this point in this whole semester, we have been kind of progressing on the whole idea of mechanics. We've looked at kinematics, the study of motion, dynamics, the study and the forces behind that motion. We looked at energy, we looked at rotational motion, we've looked at gravity, and now we wish to continue that progression to look at what we call fluids. But as we do this, we want to recall that many of the formulas and many of the ideas that we've already expressed dealing with solids will also apply to gases and liquids. Matter is normally classified in 1 of 3 states. We're familiar with solids. Solids have definite volume and shape. A liquid has definite volume but no particular shape. It takes on the shape of its container, whatever that might be. And a gas, which has no definite volume or shape, takes on the shape of its container, but it can also be compressed and it'll do whatever it has to. It'll just occupy whatever volume is given it. So those are the 3 states of matter that we're most familiar with in our macroscopic world. However, there is a 4th state of matter that's rarely talked about. It is called plasma, and it is actually a gas of charged particles, so there's some interaction between the particles. And this 4th state of matter actually consists of about 99% of the visible universe. In other words, most of this matter is residing in things like stars, and it does consist of 99% of the matter that we don't talk about. We talk about liquids, solids, and gases because that's what we see on an everyday level. Of course, there's other matter out there, dark matter, which we don't know exactly what that is. But this 4th state of matter is something that we don't talk about, and we're really not going to talk about it much more than that right now. We are going to focus on fluids. Liquids and gases are fluids, and the definition of fluid is a collection of molecules that are randomly arranged and held together by weak, cohesive forces and forces exerted by the walls of a container. In other words, a fluid takes on the shape of its container, basically gases and liquids. To deal with this new type of matter, we are going to make some definitions. One is that of density, which you should be familiar with. Density, we're designated by rho, is defined to be the mass per volume of something, and that could be applied to a solid, liquid, or gas. With this definition, we can think of the mass of something as being equal to its density times its volume. And we're going to use this quite a lot in terms of fluids. Also, we're interested in pressure. Fluids have compression type stress called pressure, and the definition of pressure is a force per area, like a stress, and it indeed is what force is applied over what cross-sectional area. If we were to submerge this object in this fluid, it would feel pressure on all the surface area of the object. So there would be different pressure at different points on this object. The unit of pressure is a Newton per meter squared, otherwise known as a Pascal. And I would note from this formula that if pressure is equal to force per area, force would be equal to a pressure times an area. And we're going to use that quite a lot so that we can utilize a lot of the dynamics that we've already introduced into fluids. So force is pressure times area. Some conceptual examples. Consider a person lying on a bed of nails. They're going to put their whole force of their weight on the bed of nails, and if you have a bunch of nails, that's much better because then you're going to have more area on the tips of those nails, and hence you're going to distribute that weight over more area, hence the pressure will be lower and you probably won't get punctured. But if you design a bed of nails and you only had one nail sticking up in your bed of nails, that's probably not a good idea, because then all your weight will go down on a very small bit of area. There'd be a lot of pressure, and it would be very uncomfortable. Here's an example from where I come from. I'm from Minnesota, and up in Minnesota, one of the things you might want to do if you're going from point A to point B across the snow is you might want to wear snowshoes, because if there's drifting snow and if it's 4 or 5 feet deep, then rather than trudging through 4 or 5 feet deep, which might take you forever, you put on the snowshoes, which increases your cross-sectional area, and hence your weight is applied over more area, and maybe you only sink 2 or 3 inches into the snow, and you can just walk along the top of the snow. Let's try an example of pressure. What is the total mass of the Earth's atmosphere? The radius of the Earth is 6.37 times 10 to the 6 meters, and the atmospheric pressure at the surface of the Earth is 1.013 times 10 to the 5 newtons per meter square. One atmosphere is 1.013 times 10 to the 5. A lot of times we'll just round that off. 10 to the 5 newtons per meter squared is approximately equal to 1 atmosphere. That's what we're experiencing at the surface of the Earth, and that's due to the weight of all the atmosphere above us bearing down on the surface of the Earth, which would be the surface of a sphere, 4 pi r squared. So we could say that the force of the atmosphere is equal to the weight of the atmosphere, the mass of the atmosphere times g, and the pressure that we feel times the area that's exerted over it would also be equal to that force of the atmosphere. Hence, we can solve this for the mass of the atmosphere. It will equal the pressure times the area divided by g. The pressure is 1 atmosphere, 1 times 10 to the 5 newtons per meter squared. The area is the surface area of the Earth, 4 pi times the radius of the Earth squared, 6.37 times 10 to the 6 meters squared, over g, 9.8. That gives us the mass of the atmosphere above us is 5.27 times 10 to the 18 kilograms. That's a lot of mass. The Earth itself is 6 times 10 to the 24 kilograms, so the Earth is approximately 10 to the 6 or 1 million times the mass of the atmosphere. So even though that's a lot of kilograms in the atmosphere, compared to the Earth itself, it's only 1 millionth of the mass of the Earth. Variation in pressure with depth. Consider this. We have a reservoir and it's full of a liquid. It could be water, and we're going to consider a section of this water within the water itself. So we're going to consider, say, a cylinder of water that's contained within the water itself. As we look at this cylinder of water within the water, we would recognize that for more or less purposes, it is in equilibrium. I mean, it might be mixing with other water, but that's going there and more water is coming in. So actually, for all practical purposes, it is a cylinder of water in equilibrium with respect to its surroundings, which is the other water and maybe the air above. So since it is in equilibrium, the net force in it must be 0. So all the forces on this cylinder of water is canceling out horizontally all the way around the cylinder, and whatever force I have on this side must be equal to the force on this side, and so net force in the horizontal direction of 0. But what about vertically? If I consider this cylinder of water vertically, well, I am going to have a force due to the atmosphere bearing down on the top, and that force would be equal to the pressure of the atmosphere times the cross-sectional area of the cylinder. So there's a force bearing down like that. There's a force due to the pressure at some depth, h, and that's over the same cross-sectional area of the cylinder, A, and so that force would be equal to that pressure times A, pushing up. And then, of course, the cylinder of water would have weight. So there's going to be a vertical force of weight going down. As a result of these three vertical forces, there is no net force in the y direction because it is basically stationary in equilibrium. So it must be true that all these forces vectorially add up to 0. We have the force going up, pressure times A from the depth of h, minus the two forces going down, atmospheric pressure, or the pressure at the top, times A, minus the weight of the cylinder of fluid. All right. We may also recognize that the mass of the fluid, considering this is fluid here, the mass of this fluid would be equal to its density times the volume of the cylinder. And the volume of the cylinder is the cross-sectional area times the height. So I'm going to substitute that in for the mass of the fluid, and we get this equation here. Pressure at some depth times A minus the pressure at the top times A minus the density of the fluid times A times the height times G equals 0. Let's divide both sides of this equals by the area and get rid of the area. 0 divided by the area would be 0. And we get this. The pressure at some depth is equal to the pressure at the top plus rho GH, where rho is the density of the fluid, G is 9.8, and H is how far we go deep into the fluid. Oftentimes, if we're looking in this particular scenario that I'm looking at here, the pressure at the top would be the atmospheric pressure bearing down, and we define P naught at 1 atmosphere as being 1.013 × 10⁵ newtons per meter squared, or pascals. So we have this wonderful equation. The pressure at a depth is equal to the pressure at the top plus rho GH. This is independent of the container shape, so you could be anywhere at that depth within the container, and the pressure would be the same at any particular depth. If you're swimming in the ocean and you go into an underwater cave, if you swim into that cave, if you're still the same depth below the top of the ocean water, you will still feel the same pressure at that depth. Pressure increases linearly with depth. That's this equation here. Our variable is h, and we have a constant in front, rho g, and then we have a y-intercept, p naught. So as we go further and further deeper, the pressure will increase proportionally with depth. Also note that if you maintain yourself at a constant height within a fluid, then if there were a change at the top, say if the atmosphere were to change in pressure at the top, that change would be felt at any depth that you happen to be. The change, you would feel the same change at your depth, because this actually should be delta P equals delta P naught plus rho G delta H, but if you maintain yourself at the same H, delta H would be 0, and simply any pressure change at the top would equal the pressure change all the way through the fluid. This is called Pascal's law, and it is the basic law, a very simple law, but a basic law that applies to hydraulics. Stated in full English, a change in the pressure applied to an enclosed liquid is transmitted undiminished to every point of the liquid and to the walls of the container. How about that? Let's say you're a fish swimming in the sea and you're maintaining the same height, and a hurricane were to pass over your head above the sea, which hurricanes usually have much lower pressure in their center than they do in the general atmosphere. Well, if that hurricane were to pass over you, you would feel that pressure change if you're in the fluid itself. And so being the fish, you would know that there was a hurricane up above you. And you probably wouldn't want to go out of the water then to go up there, because then you'd be in the hurricane. So you're just going to stay put right where you are. Here's an example applying this Pascal's law. This is a hydraulic press. We have two pistons, and we have an enclosed fluid. And any extra pressure we apply to this fluid is going to be felt all the way through the fluid. So if we were trying to lift this block over here, I could apply a force on the smaller piston over here, and that force per area will be a pressure applied to the fluid, and that pressure will be applied all the way through the fluid. So there will be another force over here on this secondary piston, and the pressure is that force per area. Well, that area is bigger, so it's going to be a bigger force. So it's still the same pressure, only on the larger area there will be a larger force. So the pressure change should be the same. Delta P1 should equal delta P2. F1 over this area over here, A1, should equal force 2 over this area over here, A2. In other words, force 2 is going to equal the ratio of area 2 to area 1 times force 1. So we're going to get a larger force with a mechanical advantage by using this enclosed fluid. How great is that? Let's try this out in a problem. The car lift. In a car lift using a service station, compressed air exerts a force on a small piston of circular cross-sectional area having a radius of 5 centimeters. This pressure is transmitted by liquid to the second piston of radius 15 centimeters. What force must the compressed air exert in order to lift a car weighing 13,300 newtons? So we're going to apply a force on this first piston to raise the car. Well, the pressure should be the same, so force 1 over area 1 should equal force 2 over area 2. So force 1 is going to equal area 1 over area 2 times the force 2. Force 2 is going to be the weight of the car. Area 1 is pi times our radius squared. I'm going to leave them in centimeters because the centimeters squared are going to cancel out. So we have pi times 5 centimeters squared over area 2, which is pi times 15 centimeters squared, times the weight of the car, 13,300 newtons. Pi's cancel out, and we'll have 1/3 squared, which is 1/9. So we need a force equal to the weight of the car divided by 9, or 1,480 newtons, which is approximately the weight of 2 adults. So if 2 of us got on this first piston, maybe if I stood on it and you stood on my shoulders, that would be enough weight to lift this car. What air pressure will produce this force? Well, we're going to use an air pressure equal to this force divided by the area of the piston. That will be 1.48 times 10 to the 3 newtons over the area of the piston, pi times 5 centimeters squared, 0.05 meters squared. And that gives us 1.88 times 10 to the 5 pascals, or approximately just a little bit less than 2 atmospheres. So if I have compressed air at 2 atmospheres, I can use that on the smaller piston to raise the car. It almost seems unfair. I'm getting some kind of mechanical advantage where I'm applying a small force and getting a large force. It seems like it would be a violation of the one equation, the rule of Moll, the conservation of energy, the first law of thermodynamics. Seems like we're violating that principle, but we're not, because we're applying work over here, and that's equal to the work over here. The thing is, though, the amount of fluid must be consistent. So in order for me to move the car with that kind of large area, to move that much volume of fluid, I'm only going to move that volume or that area a little ways to have the same volume that I'm going to have over the small piston, where I'm going to have to move it much further. So the work I'm doing over here would be F1 times some great distance. That will be the work I perform, and that's going to be equal to F2 times a smaller distance when the larger piston is going up. So the work is still the same. So we're not violating any principle of energy here. We're still going to do the same work. We're just going to move it this lesser distance with a larger force. Calculate the pressure at an ocean depth of 1,000 meters, 1 kilometer. Assume the density of seawater is 1.024 times 10 to the 3 kilograms per meter cubed, and take the atmospheric pressure, P naught, to be 1.01 times 10 to the 5 pascals. Well, the pressure at some depth is going to be the pressure at the top plus rho GH for the fluid. Pressure at the top is 1 atmosphere, 1 times 10 to the 5 newtons per meter squared. The density of the water is 1.024 times 10 to the 3, just a little bit more than pure water. Pure water would be exactly 1,000 kilograms per meter cubed. G is 9.8, and we're going to go 1,000 meters. This will give us a pressure of 1.01 times 10 to the 7 pascals, or approximately 101 atmospheres. So if you were to go 1,000 meters down, you will feel 101 atmospheres. Roughly 1 atmosphere for every 10 meters that you go down into the sea. An atmosphere at the top for atmospheric pressure, and then as you go down 10 meters, if you're 10 meters below the top of the ocean, you would feel 2 atmospheres, 1 plus 1, and then for every 10 meters, you would add 1 more atmosphere. That's a good rule of thumb. It's linear, so if I went down 5 meters in the ocean, I would feel an extra half atmosphere, so it would be 1.5 atmospheres, 1 for the pressure above, and then half atmosphere for the 5 meters of water. So that you can use that as a good rule of thumb. Every 10 meters in water is an atmosphere of pressure. Calculate the total force exerted on the outside of a circular submarine window of diameter 30 centimeters at this depth. Now if we had a window of 30 centimeters, that would be that kind of diameter right there. So we're looking at a window like this, and the force on that window would be equal to the pressure times the area. 10 to the 7 pascals times pi r squared, pi times the radius of that window squared, 0.15 meters, and that gives us a force of 700,000 newtons. That would be equivalent to if we had this window this way and I stood on it, and then 1,000 people stood on my shoulders. Approximately 1,000 people standing on this window would be the equivalent of that force on that window. And this would be if the window were horizontal or vertical or whatever. Every square inch will feel the same pressure at that depth. Just like when we're under air pressure of 1 atmosphere, every square inch of our body is feeling 15 pounds per square inch. It doesn't matter what orientation we're in, we're feeling 15 pounds per square inch all the way over all of our surface area. You know, there is a sport called free diving, and I think the record for that sport is something like 210 meters. To do that, the diver has to include the water into their body so that they can equilibrate the pressure from the inside to the outside. I don't know how they do that. They hold a breath and then they somehow bring the water in to their esophagus to try to equilibrate. It's dangerous. 210 meters would be, well, an atmosphere for every 10 meters and 1 on top. So that would be 21 atmospheres plus 1, or 22 atmospheres of pressure. Incredible that somebody would be able to dive like that, free diving on 1 breath. And as you're coming up, you have to be careful because you don't want to come up too fast with the gases dissolved into your bloodstream. You don't want to release those gases too fast because then they'll form bubbles in your bloodstream and then inhibit the flow of blood in the condition called the bends. I think it's less important for free divers as it is for divers with compressed air, like tanks. But as they get close to the top, that's where it's most dangerous, because as you're going from 3 atmospheres to 2 atmospheres to 1 atmosphere, that's quite a difference in your change in pressure as opposed to, say, 22 atmospheres to 21 atmospheres. Something to consider if you ever want to try to set the diving record. Here's a device to measure pressure, the Mercury Barometer. The inverted tube is closed. A vacuum is created when we invert the mercury, and we have pressure at the top of that column is equal to 0. But point A is at the same depth within the fluid as the open area of this barometer. And the open area has atmospheric pressure bearing down on it. And we said that if you're at the same depth within the same fluid, you have the same pressure. So point A has the same pressure as atmosphere. And it is, if we use our formula, it is at the bottom of this column with a pressure of 0 at the top plus rho GH as you go down the column. So that would mean that the pressure at A is equal to rho GH and is also equal to atmospheric pressure. So in effect, the height of the column can be calibrated to measure the pressure of the atmosphere. Because rho is a constant, G is a constant, so whatever height of the column we have corresponds to whatever air pressure we have on the outside. That is a mercury barometer. You would use mercury because it is the densest liquid that we could use, 13.6 times the density of water, and hence the height of the column wouldn't have to be so incredibly high. Of course, you wouldn't want to use mercury because it is toxic, so that would be a different consideration. Consider this problem. We have a U-tube of constant cross-sectional area open to the atmosphere. It's partially filled with mercury and partially filled with water on either end. If the equilibrium configuration of the tube is as shown in this figure, with H2 equal to 1 centimeter, determine the value of H1. In other words, the water levels are not the same because of the presence of mercury on one end of the tube as opposed to the other. But we have atmospheric pressure bearing down on either side of the tube, and those should be equal. So if we get to point A and point B, we're within the same level of one fluid, that of the mercury, and hence the pressure at those points should be the same. Well, the pressure at A is going to be equal to the pressure at the top, atmospheric pressure, plus the density of water times this total height here, which is going to be H plus H1 plus H2 times G. And the pressure at B will be equal to the pressure at the top, plus rho GH for the water, plus rho GH for the mercury. And so that's going to be the density of mercury times H2 times G, and the density of water times H times G. Bear with me, we're headed somewhere with this. These two pressures, which are at the same level within one fluid, the mercury, should be the same. So we're going to equate one to the other. We equate A to B. We can get rid of some things here. The P naught, or atmospheric pressure, cancels out. And we have a rho, so we have a rho of water, Hg, and that cancels out on either side. So we have the density of water times H1 plus H2, G, is equal to the density of mercury, H2 times G. Now the G will cancel out, and we have the density of water to the density of mercury times H1 plus H2 is equal to H2. Solve this for H1. H1 is equal to H2, density of mercury over the density of water minus 1. I just got done saying the density of mercury is 13.6 times the density of water, so this is going to be equal to 1 centimeter for H2, 13.6 divided by 1 minus 1, or 12.6 centimeters. So that is the level of the water above the level of water on the other end. If it were just one fluid, like water or any other fluid, atmospheric pressure will bear down in any opening, and it doesn't matter what the shape of your container is, the water level or the fluid level will be the same at whatever container you had, because it will be defined by the pressure at the top and the depth of the fluid. That concludes our first lecture in Chapter 14 with fluid dynamics. Our next lecture is going to be on Archimedes' principle, or the